Hello, my name is Jefferson Menegatsu, and I will now present the research in multi-contextual and multi-aspect analysis for road surface type classification through inertial sensors and deep learning. This presentation will follow these topics. Initially, I will make an introduction about the intelligent transport systems and types of sensors employed. In the sequence, I will make a brief explanation of how inertial sensors work and the dependence factors that interfere in the sampled signals. Then, I will address the three methodological steps of this research, namely data collection, pre-processing, and processing. Finally, I will present the results obtained and final considerations. In the past few decades, intelligent transport systems have emerged to improve the performance of transport systems. Among some of its most notable applications are autonomous vehicles and advanced driver assistance systems. For the operation of these applications, situational information about the transport infrastructure and its participants is required. This information is produced through a large amount of data used in artificial intelligence models. These data are collected through active approach sensors, which interact with the environment through the emission of waves to produce their data, and passive approach, which passively sample physical data and images. Thus, passive sensors are considered safe, non-polluting, and lower cost, especially considering a large-scale application. Among the methods with passive sensing, computer vision has been widely researched in recent years. However, this is not the case with inertial sensors, although a wide variety of situational information can be generated from them, as shown in the figure. The little use of this type of sensing in this research area is due to the lack of an adaptive model for recognizing situational information, since there are several dependence factors that interfere in the sample data. In this research, we focus on the classification of a road surface type, since it is one of the least researched, but one of the most important situational information. Inertial sensors are represented by accelerometers and gyroscopes. The accelerometer measures the acceleration force, and the gyroscope measures the rotation height, both on three axes. In the context of this study, this data corresponds to the vehicle's traction and its interactions with the environment. To facilitate understanding, we can make an analogy. When we travel and the vehicle passes through a pothole or a speed bump, we feel a bump, or even when driving on an unpaved street, we feel the vehicle shake. These forces acting on our bodies are the signals that the sensors sample. In the application of inertial sensors to produce classification of a road surface type, there are dependence factors that affect the sampled signals. These factors must be considered when developing an adaptable solution that can be applied to different vehicles, drivers, and environments. The four dependence properties are sensory properties, referring to sampling height, measurement range, and sensor orientation; vehicular properties, corresponding to a vehicular structure, suspension system, spring, shock absorber, and tire; driving properties, related to driving styles, maneuvers, longitudinal speed; and environmental properties, related to external environment, pavement conservation state, presence of potholes, speed bumps, other anomalies, and obstacles. All of these properties affect the amplitude and dispersion over time that analyzed data, and we considered in the methodology of this study. The first stage of the methodology consists of data collection. For this purpose, we use the sensor network illustrated in the figure. The video collected through the camera was used to assist in creating the labels of data classes. The GPS sampled the location and speed. Inertial sensors were placed in 3 points of the vehicle, being on the dashboard, near and above the suspension, and near and below the suspension to sample the acceleration force and rotation height. The sensor network was applied to 3 different vehicles, driven by 3 different drivers, in 3 different scenarios, where in each scenario there are 3 surface types: dirt, cobblestone, and asphalt segments. Each scenario also presents general variations in the environment, such as presence of irregularities and obstacles. In this way, 9 datasets were produced through the combination of vehicles, drivers, and scenarios. The second stage of this study consists of a preprocessing. In this step, experiments were defined to perform multi-contextual and multi-aspect analysis. The first type of experiment was by placement, to verify the influence of vehicle dependence property and the possibility of the module operating with data collected from different points of the vehicle. In experiment 1, data sampled near and below suspension were used. In experiment 2, data sampled near and above the suspension were used. And in experiment 3, data collected in the dashboard were used. The second type of experiment was by analysis domain, to verify the most appropriate domain among time and frequency. In the first experiment, 7 input features were used corresponding to acceleration force in 3 axes, rotation height in 3 axes, and speed. In the second experiment, the same features as in experiment 1 were used, adding composite acceleration features. In experiment 3, 357 frequency magnitude features of the 7 variables defined in experiment 1 were used, and in experiment 4, 561 frequency magnitude features of the 11 variables defined in experiment 2 were used. The third type of experiment was by context, to analyze the module's behavior when submitted data from unknown vehicle, driver, or environment. For this, we divided the 9 datasets between training and validation, so that in experiment 1, the module learns data from all vehicles and drivers for some scenarios. In experiment 2, the module learns data from all scenarios for some vehicles and some drivers. And in the experiment 3, the module learns data from some vehicles with some drivers for some scenarios, but not all vehicles with all drivers for all scenarios. Figure 9 makes this division clearer, where some vehicles, drivers, or scenarios appear only in training or validation phase. The last type of experiment was through a data window in order to consider the most adequate number of samples. Windows of 100, 200, and 300 samples were used. Finally, each experiment performed is an element of a Cartesian product among all types of experiments, including experiments by placement, analysis domain, context, or data window. After defining the experiments, classification modules were created in the third stage. In this study, we use modules based on deep learning, which are composed of several layers of processing to learn the relationship between data with different levels of abstraction. Long short-term memory, gated Heckhand unit, and convolutional neural network modules were developed. The main hypothesis of this research is that through the sampled and preprocessed data, the modules can learn the relationships and influence of the dependence factors in the data. LSTM networks are considered ideal for classifying time series and can remember important information for a short or long period of time. The LSTM-based network that we developed is illustrated in the figure and consists of an input block to receive the data, 3 recurrence and regularization blocks to learn the temporal dependencies, and a fully connected block to produce the classification. GRU networks are considered an improvement over LSTM, computationally less costly and equally efficient. In this study, the GRU-based network has the same architecture as the LSTM-based one, just exchanging the LSTM layers for GRU layers. CNN networks are characterized by the use of convolutions to extract high-level features directly from the raw data. The CNN-based network we developed is composed of an input block to receive the data, 3 convolution and regularization blocks for extracting high-level features, and a fully connected block for producing the classification. This slide details the results of the execution of all experiments on all modules. In each of the figures, there is a division by placement of inertial sensors, deep learning module type, analysis domain, input features, and data window. The displayed value corresponds to average validation accuracy for the 3 contextual experiments. Throughout the results, we observed that modules classify with good accuracy values data from different collection points. The size of the data window has little influence on the result. Half of the experiments obtained better results in the frequency domain and half in the time domain, but with very little variation. All deep learning modules performed well with little variation of accuracy value. Based on the individual analysis, we consider the best module the CNN network with the input of 7 features in the time domain and in a data window with 300 samples. The figures details the evaluation metrics. We observed that all data classes were properly treated by the module with good values of F1 score, recall, and precision. Here is a demonstration of the network running on one of the validation datasets. On the left, the video of the environment collected by the camera is shown. On the right, real-time graphs of the signals from the inertial sensors and the speed are plotted. At the bottom, the CNN network road surface classification for each collection point in the vehicle is shown, along with the probability of data class. In this study, we present the road surface type classification modules based on deep learning and inertial sensors. Deep learning modules demonstrated their ability to learn the relationships between data and dependence factors, allowing the use of modules in real road scenarios in unknown vehicles, drivers, or environments. Along with the passive approach of inertial sensors, the solution that we present is adaptable, safe, non-polluting, and low-cost, and can be applied on a large scale and in all ETS domain. This research is part of a larger and completely open-source project. All source codes, modules, and datasets are available on GitHub.